there's a couple people here. Let's see, and I think at least a few of you have an account, so if you can hear me and see me, it's really helpful if you just say hello in the chat. All right, good afternoon, everyone. Welcome back. So last time we had a bit of trouble with the video, but we managed to get it sorted in the end, and I gave a bit of a rushed lecture on the method of matched asymptotics. This time around, I'm going to keep an eye on the chat, and also I'll keep an eye on my email. Some of you might not have accounts, and you're watching just without an account. That's also okay. If there's an issue with the sound or an issue with the video, it's helpful if you either write that into the chat or if you send me an email, and then hopefully I'll catch it before the end of the talk and I can sort things out. Okay, but we have a lot to get through today, and let me kind of give you the outline of what I want to do. So the purpose of this lecture and then the next lecture, and hopefully we can wrap it up in the next two lectures, is to give you a really rushed crash course on some of the necessary tools we have for asymptotics, right? The original intent was that you could follow along even if you've only done some very basic asymptotic approximations in some of your undergraduate lectures or otherwise, and I'm hoping to stick to that intention, but that means that I have to cover some of the preliminary tools, okay? And essentially I want to finish up our content on matched asymptotic approximations and boundary value problems, and then we want to go on to integral approximations, and then that's integral approximations, integration by parts, and then Laplace's method this lecture, and then hopefully next lecture we can finish up Laplace's method and then do the most important integral approximation method, which is the method of steepest descents. Once we have all these techniques, we can then finally get back to our original programming and do some interesting exponential asymptotics. That's the goal. Okay. Now, I introduced you to this toy boundary value problem. This is a canonical boundary value problem with a singular perturbation. So epsilon here is a small parameter. You need the solution to be 0 on the left and 1 on the right. And then in the last lecture, I showed you that if epsilon gets smaller and smaller, you develop this structure where you essentially have a boundary layer near x equal to 0. You have some kind of outer region where the solution is slowly varying in that outer region that you're hoping to approximate, and then you try to rescale within the inner region to get this inner solution. Once you do that, you then have constants of integration that you need to figure out by matching. And that's what we were hoping to talk about this lecture, is the matching between the inner region and the outer region. And this is really interesting for reasons that we'll see shortly. Okay. I want to also correct that when I did the last lecture a bit of a rush, and I wrote 2y prime plus y here, and then we did everything with just y. So I want to, because this is presented in the notes, I want to make sure this is matches what you see in the notes. So this will be a factor of 2 for today's lecture, but it's basically all the same techniques. Okay. We expanded things in powers of epsilon, and then we found that the solution y is I'm going to write out the leading order solution, e to the 1 minus x, and then I'm going to also write out the epsilon correction that you can find yourselves. It's not difficult to find. And this is 1/2 times 1 minus x times e to the 1 minus x. And as usual, it's not difficult for you to go to higher order. At least for this outer region, it's not hard for you to keep on going up in powers of epsilon, and you only have to impose the one boundary condition here. The inner region is a lot harder because for the inner region, you remember this second derivative comes into play, and then you have two constants to satisfy, and the question is, well, how do you get those two constants? But if you go and make a coordinate transformation for the inner region, and the appropriate coordinate transformation we found last time was that in this inner region, we want to let little x be epsilon times big X. And so within this inner region, this big X is a fixed, it's a order 1 number. It's well scaled, and then it gets smaller and smaller with the rate of epsilon. And we had found a solution. I'm going to write it with a constant here, and then we're going to discuss where to get that constant from. And I'm going to need the order epsilon stuff as well in a minute, but it's a bit long, so I'm just going to write this plus dot dot dot. Okay. And I had argued with you just on an intuitive level how to get this constant by matching the inner and outer. I want to review that argument before we discuss the more complicated question of how you get the constants of integration in the upper orders, in the later orders. Okay? The basic idea is that to get this constant of integration, now remember that to get this leading order solution, you had to integrate a second order ODE, and you already impose one constant of integration, which is that the solution is pinned at 0 here. So that's, if you put in x equal to 0, you see, okay, I get 0. To get this constant of integration, you can use what's called Prandtl's rule, which is the inner limit of your outer solution, the limit as little x tends to 0 of y out. That's this one here, if I write y out here, is going to be the limit as your inner coordinate tends to infinity of your inner solution. So let me call that y in. Well, in this case, I've just written it as big X. That's my inner solution. And so you notice that as little x goes to 0, this approaches e. And as big X goes to infinity, this is exponentially small, and you just have c1 over 2. So that tells you that c1 is 2 times e. And that's equivalent to, so the point is that your inner solution, if I plot this quantity here, 1 minus e to the minus 2x, this is a quantity that rises rapidly, and then it saturates as big X goes to infinity. And so the point is that as the domain gets smaller and smaller, this level at infinity, you want to match the inner limit of the outer expression, this e. And it doesn't look very good as I've drawn it, but the point is that as epsilon gets smaller and smaller, it tends to look better and better. You'll also notice that at this fixed value of epsilon, if I were to just combine these two solutions together naively, it produces a kink in the middle there. But the point is that there are higher order approximations that you can account for, which will smooth everything out as epsilon goes to 0. Okay, so this is just a kind of an ad hoc rule. We can interpret it as an ad hoc rule that allows you to get the leading order constant match. But the question is, how do you impose these kind of matching rules to determine the later order constants? So let's write down what the next order correction is here, and then I'll tell you what the rule is, and it's a rule known as Van Dyke's rule of matching. 'Matching. 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 ' Okay, I'm going to, I'll erase the picture here. And then, because I need the space, I'm going to write the inner solution. I'll write that above. We won't need these ones anymore. So my inner solution, which I've called big Y of big X, let's say that I've solved for the leading constant already. That gets me an e in front. That's a 1 minus e to the minus 2 times big X. And then at the next order, this is already a little bit more complicated. It's b times 1 minus e to the minus 2 times big X minus big X times e times 1 minus e to the minus 2 times big X. Okay? So the point is that we now have this new constant of integration b, and we originally had two constants of integration, but we've set one of them so that the solution is appropriately 0 on the left edge point when big X is equal to 0. And then how to find that b. Okay? So the problem is that basically as you take this outer solution into the inner limit, into the boundary layer, then all the terms here start to become of the same order. All the higher order terms become the same order. So it's not clear, intuitively you might say, well, I'm just going to match this one with this one, and that allows me to figure out the b. But that's not the case, because this leading order expression also has correction terms when you go to the inner boundary layer. So basically, all of the terms from the outer solution start to coalesce and become of the same order, and it becomes a bit of a headache of how you actually perform the matching. And so within the literature, within the matched asymptotics literature, there is a heuristic known as Van Dyke's rule. And for the most part, outside of pathologies, this rule almost always works as a rule for matching, though you can come up with problems where there are counterexamples, but you might argue that if you account for certain weird behaviors, the rule always works. You just have to apply it in the right way. And these kind of counterexamples arise usually when you have logarithms. So when you have logs, because logs become very difficult to order appropriately with algebraic corrections, algebraic powers of epsilons, that's when applying this rule gets to be very confusing. But the Van Dyke rule is a lot easier to write it in kind of a loose, informal way. If you go to the notes that correspond to the lectures, you'll see I've written it in a more formal way, and this is the way that it's done in John Hinch's book. But the rule is basically, I'll write it down first, and then I'll say it in words, because it's a lot easier to say it in words than it is to write it out. So the rule is as follows. You take your outer, you read it as an operator. You read these two things as operators. You take your outer expansion here, and you take n terms of that outer expansion. You then rewrite it in terms of inner coordinates, and here the inner coordinate is little x is equal to epsilon times big X, and then you re-expand m terms. That should be the same as taking the m term inner expansion, rewriting it in terms of outer coordinates, taking the m term inner expansion, rewriting it in terms of outer coordinates, expanding it, and then keeping n terms. Okay, so using this and essentially going up in increasing numbers of n and m should allow you to do the match. Okay, and yeah, for the most part, this mostly always works if you do it in the right way. So I'm going to show you how you do it for this problem to get the value of b. Okay, so Now, there is sometimes an ordering at which you should kind of do these things. If I write the one term, and sometimes it's illustrated in this kind of picture, where you write the terms of your asymptotic expansion in this table, and so you have the one term approximation, the two term, the three term, the four term, and so forth, and then you have the one term, three term, four term, and so forth. And then you think of the order in which you can determine terms when you perform this procedure. So in our case, we start off with the one term outer approximation, and then we determine the leading term of the inner approximation using data from the one term outer approximation. That gave us the necessary boundary condition for our first term of the inner approximation. And then you can imagine that you might have to do this kind of procedure where the leading order inner approximation then informs you of what the outer approximation, the next term of the outer approximation is, and then so forth and so on. But the ordering in which you do this is very problem dependent. And in particular, in this problem, the outer approximation can be determined to all orders, right? Because it was a second order problem that became a first order problem, and you didn't need the boundary conditions from the inner solution to figure out all the necessary correction terms from the outer approximation. So this picture is not always giving you the exact procedure, and that's why a lot of people say the application of these ideas to these problems is a bit of an art. But in any case, if I apply the first iteration of Van Dyke's rule, I would take the one term outer approximation. Okay, so that's simply e times 1 minus e to the minus 2 times, sorry, that's my inner approximation. It's this one here, e to the 1 minus x. That's my one term outer approximation. I then rewrite that in inner variables. So that's e to the 1 minus epsilon times big X. And that's what I was showing you, this subtlety of the fact that when you go in the inner region, the leading term here has itself an epsilon expansion. And so now you can expand this one here. So this is e times 1 minus epsilon times big X plus order epsilon squared. And then you're going to take the one term inner, one term outer. So now I take the first term of the result, and that gives me e. And then that needs to match the expression if I commute those two elements. So now if I go to the one term inner, that's this one here. Let's do it with a c. Let's do it as we've written it there. E times 1 minus e to the minus 2 times big X. Okay, it's a bit bright there, isn't it? So now I'm going to rewrite this expression with the outer transformation. So there's now e times 1 minus e to the minus 2 times little x over epsilon. And I'm going to re-expand this expression here and keep only one term. But in this case, the second term here is exponentially small. So the one term expansion is basically the full expression here. So if I take the one term outer of the one term inner, I simply get e, because this is exponentially small. It's smaller than any algebraic correction. And so e matches e, and that's our matching procedure. But now we can do that with basically the two-term outer and the two-term inner. So let's do that together. So I can now take the two-term outer, and so I need to include this correction term. So that's plus epsilon 1/2 1 minus little x e to the minus 1 minus x. I then have to rewrite that in inner coordinates. So this becomes epsilon times big X this becomes epsilon times big X, this becomes epsilon times big X, and then I would might want the 2-term inner, 2-term outer. So 2-term inner, 2 terms outer. And I don't remember how, sure, let's write it out. So this is e to the 1 minus epsilon times big X plus epsilon, and there's a 1/2 1 minus epsilon times big X, e to the 1 minus epsilon times big X. And then again, you have to expand everything here in powers of epsilon. This gets you e, and then the first correction term. This gets you, and this one's easier because I only need the 2-term inner. So the leading one will be an e here. And I just need to collect all the epsilon terms. So there's going to be 1 epsilon terms from this. It'll be e times big X, I think. It'll be a minus e times big X. And then there's going to be a single epsilon term here, which is just from the unity expressions here. So it'll be a 1/2 e, I think. Okay, and of course there's other stuff as well, but we just need the 2-term inner, 2-term outer. So that's this expression here. And then you do the same thing with the inner expression. You're going to take the 2 terms here. You're going to rewrite that in terms of the outer coordinate of little x there. And then you're going to re-expand that to 2 orders. Right? So I'm going to take the 2-term inner. But that one's a bit easier, actually, because all the exponentially small things you can ignore. So I'm going to take this top expression here. I'll go ahead and ignore them. So this will be e times 1 minus da da. I'll ignore the exponentially small things. I'll have an epsilon. I have a b here that I need to keep track of. I can ignore that one there. That'll be a 1 minus dot dot dot. And then I can ignore this one here, but then this will be replaced with a minus little x over epsilon times an e. And then that will be a 1 plus dot dot dot. Okay, so I've taken my 2 terms, rewritten the big X in terms of the little x's, and then now I just have to collect everything together. So if I want the 2-term outer, 2-term inner, okay, I have e. I have epsilon divided by epsilon, so this is a minus little x times e. And then I have an epsilon times b. And all the dot to dots that you see, we're not going to produce algebraic corrections in powers of epsilon. They're going to produce exponentially small corrections. And so you didn't need it. And so then now you compare this expression here with this expression here. You see this e matches that. This matches that. And then I have a 1/2 e times epsilon should be epsilon times b. So this tells me that b should be equal to e over 2. Okay? And that's it. That's Van Dyke's rule. Okay? There's a lot more that's written about Van Dyke's rule. I mean, there's actually books on perturbation theory that focus more on application of these rules. Van Dyke wrote a famous book, I think Perturbation Theory for Fluid Mechanics. So that's the name of the book, or Singular Perturbation Theory for Fluid Mechanics, something along those lines. And his book as well shows you this method. And then after Van Dyke developed this method, which was in the 60s, I think the late 60s, there was actually a lot of research into when can you trust this rule and when can't you trust that rule. And the basic punchline is it almost always works. You have to be very careful when you do problems with logs. And you can find examples of counterexamples if you don't do it properly. Okay, but that's all we're going to need about Van Dyke's rule. As long as you know this rule exists and it allows you to match higher order terms of these kind of match asymptotic expansions, The other thing just to appreciate from this little exercise is that you can see that in even something as simple as this 2-point boundary value problem, it's actually really subtle, the details of the asymptotics. It gets really complicated, right? Because as you take one expansion out to the inner region, or you take the inner region out to the outer region, there's a very subtle reordering of terms. In the outer region, every single term of your asymptotic approximation gets smaller and smaller. That's the necessity of being asymptotic. But when you take them to a different region in space, you now have a potentially complicated and convoluted reordering of terms, where the second term becomes the same order as the first term, the third term becomes the same order as the second term, and so forth and so on. And in the exponential asymptotics bit of the course, our job is to try to come to grips with this kind of structure. Can we really understand this intrinsic structure where this second term splits into another infinite series in powers of epsilon, and then somehow everything is matched in a very complicated way between the two? And that's the beauty of asymptotics, which is you can have these really elegant, simple problems with just really deep, beautiful structure, beautiful mathematical structure. Okay, so that's basically it of this section on asymptotics of boundary value problems. And now we're going to swiftly move on to the next topic, which is integral approximations. Okay. This is really a crash course, and even in a normal, perturbation theory course, you'd be doing boundary value problems and match asymptotics over at least a few different lectures. And here we've really compressed it down to one lecture, just to give you a basic example, and then to give you a demonstration of how these techniques are done. Okay, okay. Now I want to go on to integral approximations, and again, a lot of this is going to be done via example. A word about the importance of integral approximations. So if this course is titled, Exponential Asymptotics for the Physical Sciences, and generally the problems that we are given in the physical sciences usually involve differential equations like PDEs or ODE systems of differential equations, and also integral equations as well. And that's kind of in your mind if you're thinking about classifying different problems where you can apply asymptotics to. That's usually the universe of problems that you're exposed to. Differential equations, ordinary differential equations, partial differential equations, and then integral equations. Now, most importantly, what makes the analysis of differential equations difficult is what we just saw in our example, which is that when you expand your solution into an asymptotic approximation, this is applied, kind of in a region of space, right? For example, the outer region or in the inner region. And then what you have to do when you do the analysis is then you have this potentially very complicated matching between solutions in different regions. And when you study the differential equation, that's why boundary conditions are crucial, because boundary conditions will completely change. What happens at one boundary can completely change the way your solution looks. And so there's this competition between kind of local analysis and global analysis. With an integral equation, if you have the analysis of an integral, it gets a lot easier because you don't have any boundary conditions anymore. You just have to study an integral. So in that perspective, doing asymptotics on integrals is a lot easier than doing asymptotics on differential equations. And so when it comes to the applications to exponential asymptotics, or really a lot of asymptotic machinery, the method that we use is typically to take a problem. It might be a differential equation. You then convert it to an integral equation if you can, study it in that universe, and then see if your technique, the theory that you develop for the integral equation, can inform you about how to treat the differential equation. And that's why we're doing this little expose on integral equations, because it provides us with a really powerful machinery doing the asymptotics of integrals, this powerful machinery that can hopefully then transfer to the more complicated case of a differential equation. Okay? Now, we've already seen kind of when I talked about the motivation for this course, I might have shown you integration by parts. And so when you talk about the analysis of an integral equation, we're going to, for at least now, we're going to proceed largely by example. I'm going to write down different integral equations, and then we're going to just try to understand if I can develop an asymptotic approximation of this integral. Okay? So the first example we're going to go with is this exponential integral. It's a very important function in the next few chapters because it's kind of the simplest function where you can do exponential asymptotics and derive some very interesting results. But I want to study this thing here. Let's take x to be large, and then x tends to infinity. Okay, so I want to develop an approximation for the value of this integral for different values of x on the assumption that x is large. Okay, and in this case, you can just do integration by parts. We're going to do that first, and then we're going to explain the logic about why it was a good idea to do integration by parts. So I can just rewrite this as, x to infinity of d dt of e to the minus t, and then I have minus 1 over t dt, and so that's my dv. dv is this times dt, and that's my u. So if I do integration by parts, I'll have minus e to the minus t over t, evaluated from x to infinity, have a plus, and then I have e to the minus t over 1 over t squared dt from x to infinity. Okay, and if I just keep on cranking the handle, you'll see that as long as I keep on integrating the exponential and then differentiating the quotient here, the 1 over t squared, I'm going to get a series in powers of inverse powers of t. As for this first term here, the infinity value disappears, and I'm left with the value at x. And so that gets me e to the minus x over x plus the next one, which is actually e to the minus x over x squared. It's a minus here, plus dot dot dot. So this procedure will allow me to develop a series approximation for this integral, an asymptotic approximation for this integral. They're all scaled by e to the minus x out front, and then they've got a series in inverse powers and increasing inverse powers of x, okay, with an alternating sign. So if you keep on going, the series that you developed is going to be e to the minus x times an infinite sum from 1 to infinity of minus 1 to the n plus 1 times n minus 1 factorial over x to the n. Okay, and as I explained actually in the first lecture, but we're going to revisit this in a few lectures' time, this is a divergent series. If you put in any value, any fixed value of x here, the n factorial eventually blows up. And no matter how large of an x you put in here, this thing will eventually diverge. So this is an example of a divergent sum, and that inspired our questions about convergence and divergence in the first lecture. Okay, now the way to visualize this process is actually, so instead of looking at this integral, I might want to just let x be something with an epsilon in there. A lot of us, doing asymptotics like to see epsilon. So if I let little x be big X over epsilon, then instead of looking at the limit that little x tends to infinity, I can just look at the limit that big X tends to 0, and then that allows me to write my exponential integral as so this is now big X over epsilon. You'll have an epsilon out front, and then there's a big X here, and that goes to infinity, and that's e to the minus s over epsilon over s ds under the appropriate transformation of s. Okay. The reason why I'm doing this is because I want us to be able to imagine the integral for larger values of x, and it's a bit harder to imagine integrating a function where your left endpoint goes off to infinity. I'd rather imagine a function which I fix the big X to be a number, and then I just look at what happens to this integrand when epsilon gets smaller and smaller, right? And the picture that you have is what you might have seen here. Okay, so there we are. So the graph that you see, it's actually not big enough on my screen there, but the graph that you see is the integrand at values of epsilon being, I think, 1, 0.5, and 0.2. And yeah, the idea is that as epsilon goes to 0, you get faster and faster decay because the exponential goes to minus infinity a lot faster. Okay, and basically the function is dominated. It's always biggest as left endpoint, and then it decreases monotonically to 0 as it goes to right in the integration plane. So the smaller epsilon is, the more the smaller epsilon is, you think that the dominant contribution to this integral primarily derives from basically the left endpoint. And when you do integration by parts, you're essentially extracting that endpoint value. So if I go back to this computation, that's why the whole thing works, is because I'm developing a series in inverse powers of the integration variable at its when t is equal to 0, if that makes sense. Okay? So long story short, given an integral in which you're attempting to approximate, integration by parts can sometimes work, and it's primarily going to work if the dominant contribution to the integral in the relevant limit happens near the endpoints. Okay? In the notes, I give you an example where you have to massage the function to get it into a form where you can do this integration by parts. But let's just write that down and then have a look at it. But you can read it for yourselves. So another example that I give in the notes is this function I of x is the integral from 0 to x of 1 over t to the 1/2 times e to the minus t dt. Again, x is positive and x tends to infinity. Okay? Now, this function is integrable at 0, even though it's got a mild singularity because this thing is less divergent than the harmonic function 1 over t. So that thing is integrable. And the problem is that if you do integration by parts in the way that we did it before, so you try to integrate the e to the minus t and then differentiate the t to the 1/2, then the first integration by parts gives you something like this: minus t to the minus 1/2 e to the minus t evaluated from 0 to x, and then you keep on going. And so you'll get the higher powers on the t as we did previously. But then you kind of see the problem of putting in 0 into this function here. And so this essentially gives you infinity minus infinity. So that's not too useful, just to hit it straight on with integration by parts. The way to do it is that you want to rewrite this integral so that you extract out its value at infinity itself. So instead, because the value at infinity is basically finite, right? So instead, if you write this and you subtract out the value at infinity first, but this is just a number, this first one here. And then you can then minus from x to infinity of the integrand. Now, you can kind of see in your head that this is now going to work. When you do the integration by parts here, you no longer have the problem of putting in a 0 in the 1 over t to the 1/2. And this guy here is just a number. It's this one here is root pi related to the gamma function. Okay, so sometimes, even though the behavior of that integral is exactly, it's very similar to what you in the previous example. It's just a function that decays monotonically as you go towards the right. And so you would think, again, this trick of doing integration by parts and extracting out its behavior at the endpoint is going to work. In this case, you had to do a bit of massaging, because if you were to do that, you get this kind of indeterminate series expression. Okay, so that's the first kind of technique of doing integral approximations. Notice as well that sometimes when we do integral approximations, you do it in the limit that some parameter tends to infinity. Here as x goes to infinity. Sometimes we'll do it when a parameter like epsilon tends to 0. So there you encounter integral approximations in different forms. But in general, the philosophy is the same. You are trying to develop some kind of series approximation that approximates the value of the integral in some systematic way. Okay? Right, so the next technique to doing integral approximations is a very powerful one, and known as Laplace's method. There's actually 4 techniques that you would encounter usually for integral approximations. There's integration by parts, but you might say of integration by parts is actually a younger sibling of some of the other methods. There's Laplace's method, there's the method of stationary phase, and there's the method of steepest descents. I'm not going to present to you the method of stationary phase because we're not really going to need it directly. We eventually want to get to steepest descents because that's the most important method, and Laplace's method is kind of related to the method of steepest descents. So the method of steepest descents, we're not going to do it this time around. Hopefully in the next lecture, that's the biggest brother or the biggest sister of these different methods. Okay? But the next example I want to look at are integrals of the following form. So I want to look at an integral between 2 endpoints, a and b. These endpoints can go to minus infinity and positive infinity if you like. It's going to be integrated in t space with a continuous function f of t, and then it's going to have an exponential of this form e to the x times phi of t, where x is positive. It doesn't, yeah, okay, x is positive is the easiest, okay? And x goes to infinity, okay? Now, f and phi are typically continuous and differentiable. I can tell you, that this method is going to rely upon the fact that phi is x times differentiable, so it's like you need it to be twice differentiable, I suppose. But the truth is that, we're in the business of doing it for particular functions. So I'm going to give you particular functions to try, and then you're going to see when it does work, and then you can ask, well, what happens if it doesn't satisfy those necessary conditions? The reason why these functions are really important is because they come up a lot in problems involving wave propagation. So when you take things like Fourier transforms, you end up getting this kind of integral to evaluate. So problems involving acoustics and light propagation and waves and water waves, you see these integrals again and again. And you're trying to characterize them in some limit that little x tends to infinity. Physically, this often corresponds to things like a high frequency approximation of a system. Okay, but it's not too important for us, the physics of it all, just to understand that these integrals are really important to evaluate. And the basic idea, so let's look at an example just to get an understanding of what you might want to think about. And so the example that's given in the notes is an integral from 0 to 1 of e to the minus x times t over 1 plus t. Okay, and so if you're a researcher and you want to study these kinds of problems, what do? Well, you go to Mathematica, MATLAB, or Python or whatever, and you just start plotting these things and see if you can understand what's happening when x starts to get bigger and bigger. And this is the graph that you see. So this is the last function. This is the next one. Okay, here we go. So this is the integral that I just presented you with. And this is the behavior of the integrand. So we're plotting the integrand as a function of t. It goes from 0 to 1. And the curves that you see is when little x is 5, 10, and 100. And as you can expect, if little t is 0, you just have 1. So all the graphs are pinned at 1 from the left. And on the right, everything just tends to infinity eventually as t goes to infinity. Now, as little x gets to be bigger and bigger, you end up with a faster decay in your function, right? So when little x is equal to 100, you can see that the function looks like the lowermost curve. And the key is that if you were to integrate this function, you might argue that you don't really need to approximate the function globally from 0 to 1. You just need to figure out what is happening near 0, because that's where the dominant contribution of the integral occurs. And so what you'd then like to do is take this integral, you want to rewrite it in a way that breaks it up into a contribution near 0 and away from 0, and then see if you can simplify the expressions with these two assumptions in mind. This is, you can see from the title, this is written Laplace's method endpoint, because this is a method of approximating this integral here, and for this particular case of this integral, the dominant contribution comes near from the endpoint, and then there are different versions of Laplace's method. Okay, so that's the basic roadmap of what we want to do. And so what we're going to do is we're going to split this integral up into different pieces, and then try to simplify it down. Okay, so the discussion I just gave you is suggestive that you want to split it firstly into a piece from 0 to epsilon, and epsilon is a number that, or is a parameter that you're going to have to kind of specify, though somewhat vaguely, and then a piece from epsilon to 1, and then e to the minus x times t over 1 plus t dt. Okay, and now so let's look at this secondary piece first, right? This is an integrand which is just monotonically decaying. So the largest value of this integrand is basically on the left, where it's e to the minus epsilon times t, right? And so you can essentially bound this. So the second integral that magnitude is basically less than its value at that left endpoint. And then this one here is just a number. I mean, it's less than, is like log 2 if epsilon is small. So basically, this secondary integral is exponentially small, right? So we're going to forget about it for now, because we're expecting this first integral to not be exponentially small. Okay, so we're going to focus on the first integral. And for this first integral, the key is that it's localized near 0, so you get to start expanding everything in powers of t, right, in that bottom denominator. And then you're going to expand everything and then try to evaluate things kind of term by term, and hopefully that gives you an approximation of that integral. Okay, so we essentially, our claim is that this is I of x is basically the integral from 0 to epsilon of e to the minus xt over 1 plus t dt plus exponentially small terms. So this is of order e to the minus epsilon times x. Now, this thing here is a bit difficult to interpret because the x is going to infinity, but the t is also going to the t is bounded by, is somewhere between 0 and epsilon. So it makes sense for us to do a little coordinate transformation, make this xt into something a bit easier to understand, and then hopefully that clarifies the way that we should be doing the expansions. So let's just let s be x times t. Okay, and then now we essentially have an integral of 1 over x here, and then 0 to x times epsilon in s of e to the minus s over 1 plus s over x dx. ds, sorry. Okay, and basically, as long as my s variable is such that this quantity is small, or less than 1, I can expand this guy into a series, into the geometric series. So this is 1 over x, 0 to x times epsilon, e to the minus s, and then I can expand it into a geometric series. This goes from n is equal to 0 to infinity of, I need a factor of minus 1 to the n, and then this is s over x to the n, like that. And I'm missing a ds as well. So in particular, I need s over x to be less than 1. Okay, but that can be controlled. The fact that it can be controlled as long as I have selected my epsilon to be sufficiently small. So, so note here that the largest value of the integrand is x times epsilon, and I'm just going to require that to be much less than x. So therefore, epsilon chosen in this way. Basically, the larger x is, the more local the contribution of the integral you have to consider near 0, and then you're just choosing epsilon sufficiently small to guarantee that fact. Okay. Now, under this approximation, under this assumption, you get to swap this is a uniformly convergent sum, and you can get to swap the integration and the sum. And so you can swap the integration and the sum. And basically, we're saying that you get to integrate term by term, and it's all good. Right? So you essentially have I of x now twiddles 1 over x to the n plus 1 times an integral from 0 to x times epsilon of minus s to the n times e to the minus s ds from 0 to infinity. All right, great. So now the key is to do sort of a trick with this integral. So this is an integral which is basically within a little neighborhood of the peak, right, which occurs on the left. But the idea is that you're integrating a function which is exponentially small outside of this region, right? For any values of s, which is greater than this upper bound, is exponentially small. So this integral can be essentially approximated up to exponentially small corrections just by extending this limit of x times epsilon to infinity. Okay? And that's kind of the key trick to a lot of these approximation. Basically, you took a function, you took an integrand, you expanded it around 0 to simplify a lot of the expressions. Eventually, you have this, and then now you can re-extend it to infinity because of this e to the minus s factor. So we can extend the integration to infinity and only introduce exponentially small errors. Okay, and so what we have to do is now just evaluate this integral. So I of x is just twiddles the sum from 1 to the x to the n plus 1 times the integral from 0 to infinity of minus s to the n e to the minus s ds. And this thing here is basically related to the gamma function. So in fact, let me remove I'm going to take out the minus 1 to the n here. This is just s to the n e to the minus s now. And I can use the fact that the integral of s to the n e to the minus s ds from 0 to infinity is basically a special function which is known as the gamma function. You still see that? Yeah, it's not off screen. And then this is basically n factorial. This is kind of just by definition. This is the name of that special function. You can't really simplify it any further than that. But that basically gives you the full expansion. So this is the sum from n is equal to 0 to infinity minus 1 to the n factorial over x to the n plus 1. And if you want to write that out term by term, it's 1 over x minus 1 over x squared plus 2 times 2 over x cubed plus so forth. Okay, so basically that was a lot to cover quite quickly, but let me go back and just explain to you the basic idea. In fact, let me just do it on the board, the basic idea. So the basic idea is illustrated from the picture that we drew before, that you're considering a function which is integrated, I think, from t is equal to 0 to t is equal to 1. And it's always pinned at 1 here. And in the limit that x gets bigger and bigger, the dominant contribution to the integral happens in a little section near the origin. So the first question you want to ask yourself is how big, given a value of x, like 1,000,000 or 1,000,000,000, how small of a section should you include? And that was this prescription of the epsilon. So what you did was you just rewrote this as essentially, let me write it now in this symbolic way, f of t e to the x times phi of t dt, where crucially the phi is just a monotonic decaying function. So basically it's maximized at its endpoint. You approximate this in a little epsilon bubble near the endpoint. And the thing that you didn't include is just exponentially small. It's probably off screen now, but this is exponentially small. You then Taylor expand f of t and phi of t about the endpoint. That's essentially what we did to get the geometric expansion for f of t. So you might approximate this as basically f of 0 e to the x times phi of 0 plus phi prime of 0 times t plus so forth. I feel like I'm going to go off screen again. That's probably off screen. That's a dt. If you can't read that, let me write that out properly. So this is a plus dot 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 times a dt. And then the trick is for you to notice that basically this gradient, it's actually negative, right? Because the function looks like that. So this thing here is exponentially decaying. That was the thing that we were integrating. In our case, the phi function was just minus t. So it was really simple. But you then can extend this from 0 all the way to infinity, because the function here is a decaying exponential function that's more strongly decaying as x gets to be larger and larger, and the error that you get from extending to infinity is just exponentially small. And then now you essentially have something that you can actually integrate. So the problem was, yeah. Okay? And that's basically the trick of doing this approximation when the dominant contribution comes from the left endpoint. This process where you rewrite it locally from its contribution from the endpoint, you Taylor expand the individual functions, you extend the range of integration all the way to infinity, and then that gives you the asymptotic approximation. And as you can see here, I can include higher order corrections and develop more terms in the series expansion, not just the one with f of 0. Okay? So basically the next lecture next week, we're going to do Laplace's method, but we're going to do it for the example where the dominant contribution comes from the middle, as you would probably expect. That's an important case to cover. But this essentially, as applied to the case where we took a particular function f of t and a particular function phi, it works very well when it's an endpoint. But the idea is actually going to be really similar if it's in the middle point. You're going to rewrite the integral as a left bit, a middle bit, and a right bit. You're going to isolate that middle bit, extend the range of integration now to minus infinity to positive infinity, and then you're going to come out with an integral approximation of your integral. That's going to be our wrap-up of Laplace's method next week. And then finally, we're going to cover the big sibling of all these methods, which is the method of steepest descents, which is the idea of how do you do these approximations in the complex plane. Because when you start to look in the complex plane and you start to deform your integration contour in the complex plane, it turns out that it makes life really easy and you develop a very powerful method known as the method of steepest descents. That's next week. All right, thanks for tuning in, and I'll see you soon.